So how do we attempt to understand a structure as complicated as this one? Obviously, this protein molecule has a number of different atoms, different types of atoms, the arrangement of those. If we're going to attempt to understand this, we have to start with the fundamental part, which is the atom. So the idea of atoms being the smallest part of matter has been around for thousands of years. However, it wasn't until John Dalton in 1807 that we had our first legitimate model of the atom, a model or a theory that actually explained, through several experiments and collaboration with other scientists, the laws in which matter behaved. Later on in the 19th century, J.J. Thomson came along and updated that model. And then finally, we went into the 20th century, having the model developed by Ernest Rutherford. And then we'll take a look at some other developments that happened early on in the 20th century as well in a future video. Dalton's model is pretty simple. It basically can be pictured as a solid, indestructible sphere. The parts of Dalton's model included that elements are composed of atoms. Okay, again, nothing very new. Atoms are tiny, hard, unbreakable spheres. All atoms of a given element are identical. Atoms of a given element are different from those of any other element. And atoms of different elements combine in consistent ratios to form compounds. Again, the reason that Dalton's model was the first accepted model or theory of the atom is because it was able to explain laws such as the law of constant composition and the law of conservation of mass. Next, we had J.J. Thomson's plum pudding model of the atom. J.J. Thomson, along with some other scientists, were experimenting with what were called cathode ray tubes. And basically what they do is they would take a glass tube and they would totally evacuate it from any kind of gas particles. And then they would put a high voltage at either end, so positive at one end, negative at the other end. And what would happen there is, in the absence of air, they would notice a beam of these particles going through the tube. I'm not sure how well you can see this, but they're inside the tube here. Is a beam of particles. Now, using a magnet, they could tell that the beam was deflected by a magnetic field, and they were able to determine that that beam were particles that were coming off of the atom, and that those particles had a negative charge. So now we've gone to, instead of the solid indestructible sphere, we now have these negative particles embedded in the atom, that they termed electrons, and then a positive charge spread over the whole sphere, the remaining sphere of the atom. They knew that the charge had to be balanced, an equal number of positives and negatives. So that was J.J. Thomson's plum pudding model. And then it took 80-some years for us to get from the solid indestructible sphere to the plum pudding model. Now, along this time, in the late 1800s, we were also fortunate to have some scientists working and discovering radioactivity. And the person who discovered this was Henry Becquerel in 1896. By accident, as many scientific discoveries happened, he had a mineral in a drawer with photographic paper that was inside an envelope. And what he found was that the photographic paper that had been concealed from the light actually had something that exposed it. So something must have been able to penetrate the paper outside of the film and expose it. So he was able to discover radioactive particles. These were later isolated by Marie and Marie Curie. They were awarded the Nobel Prize in Physics at one point, and Marie Curie actually went on and became the only woman scientist to win the Nobel Prize in both physics and chemistry. This these nuclear particles became of interest to Ernest Rutherford, an Australian, and he started using these to do analysis of other substances. So he took these particles that were given off by radioactive substances, and first of all, they discovered that they were deflected by a charged plate. And they discovered that these three different types of particles. There were X-rays, there were alpha rays, which he was going to use in his future experiment. Beta rays, so the alpha rays were deflected toward the negative, so they must have been positively charged. Beta rays, which turned out to be a beam of electrons deflected toward the positive plate, and then some gamma rays, which were unaffected by the charged plates. Rutherford focused these alpha particles on a thin sheet of gold foil. And what he expected to have happen was that those alpha particles would just go shooting straight through. It was kind of like shooting BBs at the plum pudding. You know, you'd expect the BBs to just go right through. They're much more dense. They're just going to go shooting right through. Well, it turned out that those alpha particles actually, some of them would go off at angles from the gold foil, and others would even bounce back away from the gold foil. So in order to explain this, Rutherford had to change the model of the atom. We had to go away from the plum pudding model and put all of the mass of the atom in the nucleus. Now, the problem here was that at this point they also did realize that the mass of the atom was basically all the protons. And so what he was asking the entire scientific community to believe was that all of that positive charge was centered in the middle of the atom, in a very, very dense area. What made this very difficult to believe is that protons being positive, those charges were going to try and repel each other. And they were able to do calculations and realize that the magnitude of the force that would be needed to hold those protons together was larger than any force known to man. Of course, now we know that force as the nuclear force. We make use of that with our nuclear energy and nuclear bombs. So over on the right, we can see then the kind of image of what Rutherford was thinking, in that most of the alpha particles indeed would go through, but you would see some of them kind of graze off of the nucleus and go at different angles, and some of them would even bounce back, such as this one here, off of the gold foil. A little bit of information about the atom. Atoms are approximately 1 to 5 angstroms in diameter, well, actually it should be diameter. And an angstrom is 10 to the minus 10th meters. And then the nucleus is about 10,000 times smaller than the atom. So really, a significant amount of the atom is really just empty space where these electrons with very little mass are moving around. So we're going to stop with our model there, but we are going to need to use some atomic structure symbols. And so here you see the symbol for a chlorine atom. The blue number on the bottom represents the atomic number. This is the number of protons that is present in the atom. And then the top number is the mass number, which is the number of protons plus neutrons. Now, interestingly, the neutron actually wasn't discovered until 1932 by a man by the name of Chadwick. So by subtraction here, we can figure out that if the chlorine atom has 17 protons and the mass number is 35, that it must have 18 neutrons. And then the final subatomic particle that we would deal with here are the electrons. And so for a neutral atom, the number of electrons has to be equal to the number of protons. Now, chlorine also has a very common ion. A species that has an ion would be something that has either gained or lost electrons. So chlorine, in an ideal world, likes to gain an electron. So if chlorine had gained an electron, we would have Cl minus. It still has to have 17 protons because it's chlorine. If you change the number of protons, you would change the element itself. And 35 for the mass number. Okay. Now, another term that we need to be familiar with are isotopes. It turns out that chlorine can also have a different number of neutrons. So if we have a chlorine atom, and again, it has to have 17 protons, the atomic number has to be 17, but it turns out that you could also have a mass number of 37. Well, a mass number of 37 would mean that you would have 20 neutrons. Okay. So these two chlorines, the chlorine 35 and the chlorine 37, we would refer to those as isotopes. Much the same way we would refer to two children that were born together as twins. So these would be isotopes. So we'll want to practice using some of these symbols just to make sure that given the symbol we can calculate how many protons, how many neutrons, how many electrons, and vice versa. If we knew the protons, neutrons, and electrons, we could create the symbol for the atom.